All right, so last week we finished talking about limits and we talked about continuity. And so we realized that continuous functions are really the only ones that we're going to be able to talk about in this class, because if we leave the world of continuous functions, you get those really weird functions that jump up and down quite a bit. And who knows what's going on with those things? I'll leave that to the brainiacs over at MIT. Okay. So if you know you're talking about continuous functions, then you get some very nice theorems. And so we're going to start off by talking about a couple of these. And the first one, which during the end of the quiz I heard everybody who's seen it before loves this theorem so much, is the intermediate value theorem. And the second theorem we want to talk about is called the extreme value theorem. Although, I think these days they dropped the E. All right. So what does the intermediate value theorem say? Well, it's actually very easy. If I want to walk over to the wall, right, I'm going to go in a straight line. If you imagine an imaginary line going from the end of this desk to the board, I can't get to the wall without crossing the line, right? There's just no way. If I'm going straight to it, cross it, right? There's just no possible way around it. I have to cross it. Does everybody agree about it? There's no way I can get through it without crossing. Yeah?
And you jump over it.
Now, but imagine now, instead of it just being a little line, right, it's just a plane that goes all the way up to the ceiling. Right? So there's no jumping around it. Okay? Have to cross it somehow.
Take a tunnel.
Take a tunnel. Right? The plane goes all the way. You guys think he's joking, but you know what? This is exactly what mathematicians do. Mathematicians look at something and start saying, okay, now how can I get around that? Build a tunnel, right? They think outside the box. So what Kevin's doing, as smart alecky as it is, it's actually exactly what mathematicians would do in this situation. So it's okay. That's why I don't, get a switch off the tree like they did in school. Okay, so how do we write this up in some sort of meaningful way? Well, you need hypotheses and conclusions. Right? That's what any sort of theorem is going to look like. Okay, fine. What kind of hypotheses do you need? Right, well, there's something very special about me walking through this line. Right? And that is, I can't, for instance, teleport. Right? Imagine if I had a little transporter over on Star Trek, right? And I say, beam me over, Scotty, right? And instead of going up to the ship, I just disappear and I reappear over here. Okay. If I could do that, then I wouldn't have to cross this line, right? Okay. Why can't I do that? Okay. The physics of transporters is not what we really want to get into. But I mean, the point is that when I move, right, I can't just disappear and reappear somewhere else. Okay. If I want to go from point A to point B, I have to go in, you might say, a continuous way. Right? I'm always there. Okay? I can't just jump and be somewhere else. Okay. So think about this function y equals 1 over x. It starts off as a function, right, which is negative. Okay? It's always negative over here. And then over here it becomes a positive function. Okay? So you'd think if you're going to go from negative to positive, at some point you got to cross 0. Right? But why doesn't it? Well, what's the problem here? At x equals 0, okay, this function doesn't even exist. Right? So it's not continuous at that point. Okay, so there's somehow a jump, right? Or let's do a piecewise defined function. going to be, well, let's see, how about f of x equals x when x is less than 0. So it's going to go like this. And 0, we get a little hole. And then it's going to jump up to 1 and become x plus 1 when x is greater than or equal to 0. Right? And you think, okay, this function is always negative, and this one already is up at least 1. If the function was continuous, it would have to hit all the points in between. Right? But because it's not continuous at this point, right, it has a jump, it doesn't have to hit any of the points in the middle. Okay? This is like, I mean, you think about it. You're living your life, and then boom, you get transported up to 1. Okay? Then you can skip walking through the line. Right? Now let's just recall, why isn't this continuous from the definitional point of view?
The limits on both sides are equal.
Exactly, right? What's the limit of this function as you get to 0? 0. What's the limit of this function as you approach 0 from this side? 1. 1. Right? The limits aren't the same, so it's not continuous at that point. Okay? I mean, the limit doesn't even exist at 0. Right? You only get one-sided limits, so it certainly can't be continuous. Okay. So, if we're going to say something meaningful, like I walk from here to there and I have to cross through some point in the middle, I'm going to need to have continuous functions, right, if I want to get the right conclusion. So we're going to start with, I'm just going to abbreviate IVT for intermediate value here. Say let f be a continuous function. That is crucial. Anything meaningful I want to say is going to rely on that. Now, you'll notice here there's a real problem at x equals 0 for continuity. But if I move away from 0, there's no problems. Right? If you forget about 0, this function is continuous. Agreed? I mean, if I just restrict myself to, say, 1 to 5, right? I just look in this little window. That's a continuous function. There's no problem there. So let me just say let f be a continuous function on an interval. And we'll call it I. And I don't mean a closed interval or an open interval or just any interval. Okay, so from 2 to 6, whether you include the endpoints or not. Just assume it's continuous. What do we want to say? We want to say that if we have our function somewhere, a function over here somewhere else, then it's got to hit a point in between. Okay. So if, let's say if A and B are points in the interval, such that, let's say f of A is less than or equal actually, let's even let me add a point in the middle. Let's just say f of A is less than or equal to L is less than or equal to f of B. Okay, so here you would think f of A is almost 0. Well, that's not a good one. Let's look over here. Let's put a 1 there and a 5 there. Okay, there's f of 1. Okay, there's f of 5. And I'm going to choose some point in the middle. I'll call that L. So that's all I'm saying. In some order, I have f of A less than or equal to L, less than or equal to f of B. Then, there exists some C in the interval I. such that f of c is equal to m. So in this picture, there would be my c. Because this L corresponds to that point, not your f of c. So we've now translated something which is intuitively pretty clear into a mathematical statement. We can actually be a little stronger here. This c that you choose is not just in the interval. Right? You can actually choose it in between a and b. So we can even make this stronger. Well, let's just assume for now, it doesn't hurt anything. Let's assume that a is less than b. Then we can actually choose c to be somewhere in the interval from a to b. Doesn't hurt anything. Okay? Any questions about this formulation? Okay, let's see a quick corollary of it and then use it. All right, let's let f be a continuous function. On an interval I. And let a be less than b. The elements in this interval I, such that f of a is less than 0, say less than or equal, and f of b is greater than or equal to 0. Okay? So the function is negative, and then it becomes positive. There exists a point C in the interval, actually from A to B, such that f of C is 0. Okay, if you've never seen the word corollary, this just is another theorem which follows immediately from a previous theorem. So that's our intermediate value theorem, and then this statement follows immediately from this one, and we call it corollary. Or when I was in the UK, they called it corollary. Corollary. But it's corollary. Don't let those Brits fool you. Okay. Now, why does this follow as a corollary from this theorem? Well, we're just replacing L with 0. Right? Everything else is the same in the statement. Okay, so let's see why this is potentially useful. All right, I have a function, and I look at some point and say, that's negative there. And then I move over here and I look at the point, and I say, well, that there is positive. It was negative, and now it's positive. What can I say about this function? At some point it was 0, right? I assume this is a nice continuous function, okay? Not trying to fool you with a graph, it really is continuous. Okay? Well, then we know that there's a 0 somewhere, right? And it's in between these points. There's your A, there's your B, that point is your C. Okay? This showed up on the pre-final. I don't remember the exact function, so let's just make one up. Let's look at f of x equals x cubed plus x plus 1. Okay? Now, I don't know what the roots of this polynomial are. Yeah? I mean, what do you do with it? How do you find the roots? I don't know. But here's what I can do. Right? Let's look at f of minus 1. So you get minus 1 cubed